Now that we have introduced the reciprocal lattice and discussed how the Miller indices are defined, including the important fact that the reciprocal lattice vector G sub HKL is perpendicular to the HKL plane, let's look at the reciprocal lattice from another very important perspective, which is the Fourier-series perspective. Suppose we have some physical quantity in a crystal represented by a function f of r, where r is the position vector. The physical quantity could be electron density, atomic potential, charge distribution, and magnetic moment density. Because the crystal is periodic, this function must satisfy the translational symmetry of the direct lattice. This means that f of r must repeat itself for any lattice translation vector. Now, since f of r is a periodic function, it can always be expressed as a Fourier series, as shown in this expression, where a sub k are the Fourier series coefficients. This expression is nothing but a weighted sum of all plane waves, expressed as e to the I k dot r, each characterized by a wave vector k. At first glance, it may seem that k could be any wave vector, but the crystal periodicity imposes a strong restriction. If we translate the position by a lattice translation vector, capital R, then f of r plus capital R can be written as shown in this expression, where the distributive property of the inner product has been applied. For this translated function to equal the original function for arbitrary position vector r, which is expressed as f of r, the factor e to the I k dot capital R must be equal to 1. So the allowed wave vectors must satisfy this expression, e to the I k dot capital R equals 1. Or equivalently, k dot capital R equals an integral multiple of 2 pi. So this is the key result on this page. It tells us that only certain wave vectors are compatible with the translational symmetry of the crystal. So the main message of this page is a periodic function in a crystal cannot contain arbitrary Fourier components. Its Fourier expansion is restricted to wave vectors that satisfy the lattice periodicity condition. Now let's show explicitly that the allowed wave vectors in the Fourier expansion are precisely the reciprocal lattice vectors. Recall that a direct lattice translation vector, capital R, can be written as a linear combination of integral multiples of primitive vectors, as shown in this expression. On the other hand, a reciprocal lattice vector, capital G, can be written as shown, where HKL, they are integers. Let's now check whether such a G vector satisfies the condition we just derived on the previous page. We evaluate e to the ig dot capital R, substituting the expressions for capital G and capital R. We obtain the expression shown here. Using the defining relation of reciprocal basis vectors, this simplifies to the expression shown here. Since h, k, l, and u1, u2, u3 are all integers, the quantity in the parentheses is an integer. Therefore, e to the ig dot capital R equals 1. It must be equal to 1. So every reciprocal lattice vector automatically satisfies the periodicity requirement. But now we must also show the converse. If a wave vector k satisfies k dot capital R equals an integral multiple of 2 pi for every lattice translation vector capital R, then the wave vector k must itself be a reciprocal lattice vector. To do that, we expand the wave vector k in the reciprocal basis as shown in this expression, where c sub I equals 1, 2, and 3 are undetermined coefficients. Then k dot r can be written as shown. Using again b sub I dot a sub j equals 2 pi times the quantical delta function, we obtain the expression shown here, which is the sum over I of 2 pi times ci ui. So for the condition to hold, which is k dot capital R equals 2m pi, the expression shown here must be an integer. This is the crucial point that will be completed on the next page. Let's continue from the result at the end of the previous page, which is the sum over I of ci times ui, where I equals 1, 2, and 3 must be an integer for arbitrary integers u1, u2, and u3. Now we ask, what does this imply about the coefficients c1, c2, and c3? The answer is that each coefficient must itself be an integer. Why? Because the translation vector capital R is arbitrary, which means the integers u1, u2, and u3 are arbitrary. Even if one of the coefficients were fractional, then the sum could be an integer for some special choice of u1, u2, and u3, but not for all choices. Here we provide a very helpful example. Suppose c1 equals 1 over 3, c2 equals 3 over 4, and c3 equals 2 over 7. Then for one particular choice, such as u1 equals 3, u2 equals 4, and u3 equals 7, the sum becomes an integer, which is 6 in this example. But that is only an accident for that specific choice. Apparently, the sum of I of ci times ui won't be an integer if u1, u2, and u3 are not integral multiples of 3, 4, and 7 simultaneously. So if we choose a different set of integers u1, u2, and u3, the sum will generally not remain an integer. Therefore, such fractional coefficients are not allowed. Hence, the only way for the sum over I of ci times ui to be an integer for all integer values of u1, u2, and u3 is for all the coefficients c1, c2, and c3 themselves to be integers. So we conclude that the set of reciprocal lattice vectors corresponds to that of the wave vectors used in the Fourier series expansion of any physical quantity that is periodic in the direct lattice. In other words, the allowed wave vectors appearing in the Fourier expansion of any physical quantity periodic in the direct lattice are exactly the reciprocal lattice vectors. This is a very deep and important conclusion. It means the reciprocal lattice is not merely a geometric construction. It is also the natural set of wave vectors that appears when we describe crystal periodic quantities in Fourier space. So from the standpoint of mathematics, the direct lattice describes periodicity in real space, while the reciprocal lattice provides the allowed Fourier components of that periodicity. This is precisely why reciprocal space plays such a central role in solid-state physics, diffraction theory, and later in band theory.